Hello, friends. Have you ever watched a recursive function run and wondered how it knows exactly where to continue after each call? Like, you call a function, it calls itself again, and somehow, when it is done, it picks right back up where it left off. That feels almost magical, but it is not magic at all. The answer is a structure your program uses constantly, called the call stack. The call stack is what gives every function call its own private workspace, its own memory of where to return. Once you see how it works, recursion stops being mysterious and starts making perfect sense. In this video, we are going to build that understanding from the ground up, step by step. Alright, before we get to memory, let us understand what a stack actually is. Think about a stack of plates in a cafeteria. You put a clean plate on top, that is called a push. When someone needs a plate, they take from the top. That is called a pop. You never grab a plate from the middle or the bottom. That is the defining rule of a stack. Last in, first out, or LIFO. Whatever was added most recently is the first thing removed. That is it. Two operations, push and pop, and a strict ordering rule. Stacks sound simple, and they are, but that simplicity is exactly what makes them so powerful and predictable. Now let us look at where your program uses this structure automatically, every time a function is called. Here is the interesting part. Your computer uses an actual stack structure in memory to manage function calls. Every time a function is called, the program creates what is called a stack frame and pushes it onto the call stack. That frame holds three important things: the function's local variables, its parameters, and a return address, meaning the exact location in the code to go back to when this function finishes. When a second function is called from inside the first, a new frame is pushed on top. The original frame stays on the stack, patiently waiting. This is precisely how a function remembers where it left off. Its frame is just sitting there, untouched, until execution returns to it. In our example, calling factorial of 4 will push 4 frames total. Let us now look at a real recursive function, so we can trace this in action. Let me show you the function we will trace through the rest of this video. It is a classic, computing a factorial. The function is called factorial, and it takes one integer parameter named n. Line 2 is the base case. If n is equal to 1, return 1 immediately. That is the exit condition. Without it, the function would call itself forever. Line 4 is the recursive case. Return n multiplied by factorial of n minus 1. So factorial of 4 returns 4 times factorial of 3, which returns 3 times factorial of 2, and so on. Each call makes the problem one step smaller, driving toward that base case. We will call this, with n equal to 4. Now watch exactly what happens on the call stack, as each of those calls is made. Now let us watch the call stack grow. We start by calling factorial of 4. The program pushes a frame for factorial of 4 onto the stack. It stores n equal to 4, and a return address back to wherever main called us from. Inside that call, line 4 runs and calls factorial of 3. A new frame is pushed on top, next n equals 3, waiting to return to factorial of 4. That triggers factorial of 2, another frame pushed, n equals 2. That triggers factorial of 1. One more frame pushed, n equals 1. Now we have 4 frames on the stack, each one paused and waiting. The top frame holds factorial of 1, and n is equal to 1. That means the base case is about to be triggered. This is the turning point. Next, the stack starts to unwind. Here is where it all comes together. Factorial of 1 hits the base case. N is equal to 1, so it returns 1 immediately. Its frame is popped off the stack. Now the top frame is factorial of 2. It was waiting for that return value, so it computes 2 times 1, which equals 2, and returns that. Its frame pops. Factorial of 3 resumes. It computes 3 times 2, which equals 6, and pops. Finally, factorial of 4 computes 4 times 6, which equals 24, and that frame pops too. The stack is empty, and the answer 24 travels back to main. Each frame remembered its own value of n the entire time, tucked safely in its stack frame. That is the beauty of the call stack working alongside recursion. Alright, let us bring it all together. Every time a function is called, a frame is pushed onto the call stack, holding that function's local variables, its parameters, and its return address. When the function finishes, its frame is popped, and execution returns exactly where it left off. Recursion works because the stack handles all of that bookkeeping automatically. One last thing worth knowing: if a recursive function has no valid base case, it never stops calling itself. Frames keep getting pushed until the stack runs out of memory. That is called a stack overflow, and it crashes your program. So always define a clear base case. The key takeaway: the call stack is not a mystery. It is an elegant, automatic system that gives every function call its own memory and its own place to return. Thanks for watching, friends.